continue. Right, simple harmonic motion. If you can write that down, please. Chu, could you please turn to the left? Thank you. Where does KJ live? No, but mostly where does he live?
Dublin.
Ah. Why didn't you say so? Where in Dublin? We don't know where he lives?
He lives up the Easy River.
He's by the Liffey.
Over?
Okay.
Not sure.
He must really like physics if he's getting a taxi to get here.
Oh, taxi. Yes. I love too expensive. Okay.
No, it's not too expensive. It's just €8 to go to the city center.
€8, true. But it's, it's only... It's only 2.7 kilometers to the city centre. That's a comfortable 25-minute walk.
I mean, yeah.
And what about all these protein shakes you're taking? You should be walking that in minutes.
That's the good point. I like to walk inside the gym, not the outside.
Oh, you only walk inside.
Yeah. And then the point is, I have to go to gym, and that's 50 minutes from here. And I already walk outside 50 minutes, and then inside I walk 40 minutes. And that's a lot.
But you can walk to the city centre for free.
Oh no, I don't want to.
Okay.
I hate hopeless.
So you pay to go to the gym to walk.
Yeah. But not only walk, I spend 2 hours in the gym.
Rich girl.
After class.
Sure. Well?
2 hours doing what?
1 hour or working,
Weights.
running.
All right.
And 5 o'clock.
Cardio.
1 hour for leg training.
Very good, very good. So you'll be super strong by the end of the year.
That's my goal.
That's your plan. Good. Fly Fit, isn't it?
Fly Fit, okay. 29.
Anyone else go to Fly Fit?
No.
That's a better question, yeah. Anyone else go to the gym?
Yeah, I plan to.
You plan to? Very different.
For 2 months.
That's not the same as going to the gym.
And that's why
Definitely not.
have Zumba dance class, and that's so interesting.
Oh, okay. Maybe one day you'll see Sean there. He's planning to go.
Well,
Maybe. Okay. Simple harmonic motion now. You got that? Let's see. Let me. Right. Continuing now. So, just like circular motion, there's quite a bit of formulas to get through. There's a lot to do, yeah. Okay, so this obviously is a spring, and this is a special type of motion in physics, and we call this type of motion simple harmonic motion. Just like with circular motion, it's a special force that causes it. So the spring moves up and down in this sort of motion, and just like with circular motion, it's caused by a special type of force. What's so special about this force? What's special about it is that if it's moving by simple harmonic motion, then the force is proportional to the displacement and acts in the direction opposite of that displacement. So I'll give you a minute to write this down, but I just want to explain this with a little picture here. If this is moving in simple harmonic motion back and forth, what we're saying is there's a force here, and the force is towards the center, and also that the force, or the acceleration, same thing really, what did I go with here? The force, is proportional to the displacement. So in other words, the bigger this is, the bigger the F. So if this is twice as big, then the F will be twice as big. You know what I mean? Like, for example, like if the ball was here, then because this distance is twice as big, then the force here will be twice as big. That's what I mean when I say proportional. Do you understand this word? Sean, you look confused. And it also acts in the direction opposite of the displacement. So what I mean is, when the ball is on the right, the force is to the left. And when the ball is on the left, the force is to the right. Okay, so this definition now, please write it down carefully. You okay down there?
No.
Cold? I don't know if that heater works. You might have to go to that one over there. If you wish, you can move your desk up to the heater. Are you sure?
Yeah, I don't change my clothes then.
Okay. Tell them what? What? I don't know what you're saying.
Well, I mean, how to clean our home.
About what?
About this room.
It's a great room.
Yeah, it's great. It's great.
It's not too cold. Come on.
Let's just begin 2 and 3.
I can't because the biology students are there.
No, B3
Why don't we do it from here? Change the room.
Good idea.
Yeah, because we have to take chemistry after this physics and that room.
So do the biology students.
I don't know the biology.
Yeah.
It's good to be staying 4 hours in the same building.
You don't need the rule.
Good.
Exercise.
Yes. It's really becoming. It's really working out. Maybe I'll say something to Connell.
Yeah, that's good.
Yeah.
It's kind of far from my room, but
Yeah. Yeah.
I mean, it's close to both spots. It's both closer to you guys.
I prefer Schneider, so I can wake up late.
Oh, yeah.
Yeah. Continue. Okay. Imagine a spring pulled out and then released. What would the velocity time graph look like? Well, if you pull the spring down and let go, first it's going slow, then faster, 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 and then it slows down, and then it goes faster again, because it's going slower, stop, yeah, faster, it's switching between going slow and fast. So the graph would look, something like this, going between fast and slow as it's moving up and down. I don't think there's much to say here. You all get the picture, yeah? In simple harmonic motion, we have 3 terms that we were also used in circular motion. So the 3 similar terms is F. So the F means the same thing. In circular motion, if I said 2 hertz, that would mean in 1 second,
Yeah. 1.
2 for 2 hertz. means in 1 second 2 oscillations. 3 hertz, 3 in 1 second. Same for simple harmonic motion. 2 hertz means this: out, back in 1 second. It's the same meaning. What else is the same? The time is the same. The periodic time is the time for 1 oscillation, and something else is the same. I wonder if you... No. Think about the formulas for F and T. What might be the same? What's that called? Yes. The angular velocity, the omega, that's the same. However, the omega is a bit peculiar here, because what was the units for omega? Not hertz per second? Yeah, what was the unit for omega? Radians per second. How quickly the angle changes. If there is no angle, what the heck does the omega mean?
0.
No, not 0. Not 0. It's something to do with the displacement, but what exactly? Like, it's still radians per second, but how could it be a radian per second if there is no angle? Like, what could it be? Any ideas?
No.
No. Huh? No. It will depend on the F and the T. What? There's no angles, so what does it mean? Well, let me show you with an example. So this actually is a good example. This part of the train is moving with simple harmonic motion. This part of the train is moving with circular motion. This part has an omega, 1 radian per second, for example. This motion causes this motion, or this motion causes this motion. The omega here is the same as the omega here. In other words, if the simple harmonic motion was connected to a wheel, then the omega would be the omega for the wheel. And another example which my teacher gave me, which I found useful, but quite old example. Imagine that you had a wheel on the ground, and you have a candle on it. Yes, I know, a candle. Yes, with a little flame. And here you have a wall, and this candle makes a little shadow on the wall. As this turns, this will move left and right on the wall. This motion is simple harmonic motion. This motion is circular. The omega here is actually the omega here. So there is this relationship between circle and simple. In fact, simple harmonic motion is really kind of like circular motion, except circular motion is in 2 dimensions, simple harmonic motion is in 1 dimension. You see that there is a relationship between the two, quite an interesting relationship. So I don't know if you want to draw this, or if you want to draw this, but I think it is worth saying something in your notebook. Yeah? Are you drawing the train or the candle? You're going for the candle.
The candle.
Okay, alright, fine.
This one is easy to understand.
This is easier to understand than the train. That's funny, because I would have thought the train was easier. So I guess my physics teacher gave me a good example. Got that? Continue? Okay. And if you actually want, there's an animation online. You could type this in later if you wanted to see this in action. Okay, so some terms. So equilibrium or origin, that means the center of the simple harmonic motion. Amplitude A, does anyone know what that word might mean? You know this, Monica?
The height.
Kind of like, yeah, like a height, but not only a height. Yeah, I think you have the right idea. Amplitude refers to how far out it can be at most from the center. The maximum displacement is the amplitude. Velocity, okay, you know that. Angular frequency or angular velocity, you know that. Frequency, you know. Time, you know. So the first two are new words. I'd like you to write the first two down, please. Yeah, it's a synonym. You can say angular velocity or angular frequency or angular speed. Okay, continue. You got those terms? Jerry? No. Got that? Jerry? Oh, Jerry, you break my heart. Okay. No, it's okay.
Right?
Sure.
No. We'll finish at 10:40 instead of taking a break.
Why?
Because I'm in the middle and I'm on a roll here.
Okay.
This way gives you 20 minutes before your next class.
We should wait
No, we'll leave KJ behind.
Okay.
If you hear this later, KJ, I tried to stop, but they just wanted me to keep going.
That's why.
What's that? Shh, there's a lot of noise in the background here. Okay, continuing. Yep.
This can be a negative value for the amplitude.
It cannot. Amplitude is the biggest positive displacement. Yeah. Okay. When the mass is at its maximum displacement, it is at rest. So as it's moving left and right, when it's furthest out, it's at rest. Come in, KJ. Come in.
Welcome.
We're waiting for you.
Good taxi journey? How much did the taxi cost?
12.
12?
Yes.
Where? I'm so there. Okay. So, when the mass is at its maximum displacement, it's at rest. Therefore, it has no kinetic energy. But it still has energy. So, where did the energy go? It didn't lose the energy. Yeah. So, if you think about it, as the mass moves left and right, here it's at rest. Its kinetic energy is 0. Here it's going its fastest, so the kinetic energy is definitely not 0. But you don't lose energy. So what's happening is there's a potential energy here which is 0, and here which must be not 0. In other words, they must be exchanging energy back and forth. So it has only potential energy. As it starts to move, its potential energy becomes kinetic energy, and vice versa. When it's at the origin, it has no potential energy. It has only kinetic energy. This is when it's travelling its fastest. So below is the graph of the energy, which I'll explain now, just before we continue. So here, if you can see, when it's at its furthest out, it has no kinetic energy because it's at rest. But as the ball moves back towards the centre, it's getting faster and faster. So what's happening to the kinetic energy? It's increasing. Now what's the formula? It's a half mv squared. So that's why it's a curve shape, it's a quadratic. But as the kinetic energy increases, then it must be losing potential energy. So the potential energy decreases and is at 0 at the centre here. If you add the two together, you get total energy. Why is this a flat line?
Same.
Yeah, it doesn't change. Conservation of energy. Conservation of energy means that the total stays the same. So if you were like here, and you add the kinetic with the potential, the total, this plus this, will equal the same. Okay? They have asked the students to draw this graph in the exam. I think they've asked it maybe 4 or 5 times, maybe 4 times. So it's common enough. And students sometimes get this right, sometimes they make a mistake. I need you to copy this graph in your notebook carefully. Total. Wait, before you copy, there's one thing missing from this graph I just saw. I have total, I have potential, I have kinetic, but I never actually marked here, this is the amplitude, A. And this here, minus A on the axis. Yeah, so like if the amplitude is 2 meters, then this is when the x is 2 and when the x is minus 2. Okay, draw please.
Why didn't we start with tutorial?
We did the tutorial first.
You finished it?
Oh yeah. We had a great time, didn't we? Yeah. Answered all the questions, discovered things about ourselves, so that was great. So, yes, try your best to draw this neatly, please.
So that's a positive amplitude and negative amplitude.
Yeah, I shouldn't really say positive and negative amplitude. The amplitude is only positive. The displacement can be plus A or minus A. Yeah. Yes. Continue. Yeah. Continue. Oh. Continue. Okay. So, here are some more graphs, but again, we've already seen this a little bit. The first one is displacement, so it moves up, moves down, moves up, moves down. Second one is velocity, so it's fast, at rest, opposite direction. And interestingly, acceleration also has the same shape. So the only thing I want to show you here is that the displacement, the velocity, and the acceleration, they all have this up, down, fast, slow, positive, negative behavior. That's the key thing here. So now, after we talked a little bit about it, we can finally look at some formulas. You'll be pleased to know that some of the formulas are the same. So T is still 1 over F, or 2 pi over omega. This is the new formula for today. The acceleration is not v squared over r. It's now minus omega squared s. S for displacement, or x, whichever you prefer. Okay. Now, the next formula is what is the S for a particular time. Now, please note, this S is A sine omega t, but that's if it's starting from the equilibrium. What I mean, when we have our motion, there's two ways to start it. It either starts from the middle and goes back and forth, or it could start from the end and swing back and forth. So, if I just, the two situations are this. We can start from the inside, which means it starts here, and then goes back and forth like that. Or the other situation is it starts here, and goes all the way out and all the way back. Okay? Different formulas for both. So here it's sine if we start from the middle, otherwise it's cos. The next formula is the velocity. It's A omega cos omega t, again if it starts from the middle, otherwise it's sine. Now actually that's a typo there, I should have said minus sine. Can you just stick a minus in front of that? That should be a minus there, minus sign. Minus here. So I don't forget, I'll just open this notes up. Okay. Please make the minus here, that's a minus sign. Whoops. Okay, continue. The next, and then the next formula is V. This formula you don't require to know the time, you just need to know where the mass is. The reason for the plus and minus is because it's a velocity, so if it was moving to the right, it would be a plus, and if it's moving to the left, it's a minus. If the question just asked for the speed, then you don't care about the plus or the minus. Please note the difference between these two. In this one, I don't need the time. In the previous one, I do need the time. This is the key difference between Formula 5 and Formula 6. The next one is the formula for potential energy. It's half m omega squared s squared. So when it's at the equilibrium, S is 0. When S is 0, what's PE? No? What's potential energy when S is 0? It's 0, which is what we said earlier. So when is potential energy biggest? When kinetic energy is 0. And when will that happen? For what value of S? The maximum, which is called amplitude. So the maximum potential energy is a half m omega squared a squared. But that's also the same as the total energy. Because when the potential energy is maximum, do we have any kinetic energy? No. So it means all of that potential energy is the total energy. So if you want, you can think about it, there's an extra formula. Total energy is a half m omega squared amplitude squared. If you want, you can think about this as another formula, formula 8, and not necessary, but if it makes you happy and you sleep better at night, you can think of this. Okay. Got that? Just this with an amplitude. Okay. Now, next. In the real world, the motion is more like this. Because in real life, if we have simple harmonic motion, it doesn't continue forever like this. It will slow down. We call this damping. This is the simple harmonic motion slowing down due to friction. This is what would happen in the real world. I think in the exam I maybe have seen them ask once to draw the simple harmonic motion if it is being damped. Okay, so I would like you to draw this with the title damped simple harmonic motion or dampening, whichever you prefer. So the word damp here means to cause it to slow down due to friction. Damp also has another meaning in the English. It means wet. Clearly that's not what I mean here. Okay, can you draw this? This is called dampen. Okay, continue. Yep. Right, next now. This is an interesting type of problem, which I'll draw again. Or, well, I don't have to draw, I can explain it right here. This is two simple harmonic motion masses undergoing two simple harmonic... Grammar. Here we have two masses. Each are undergoing simple harmonic motion. So can you see, this one is vibrating left and right. This one is vibrating left and right. And we'll call this one small x and this one big X. But, key, they're connected. So this motion here will affect this motion. So if I just redraw this one here, I have this one here, it's moving with simple harmonic motion. This one here is moving with simple harmonic motion, and they're connected. So we'll call this one minus A1 plus A1 minus A2 plus A2. We'll say that this one has an omega 1, an omega 2, F1, F2, T1, T2, and obviously it's moving back and forth with an X and a B, but I don't care about that. This has an A1, this has an A2. There will be some effect of this on this. It will affect it. So my question is, I want to know how can I make this bigger? If I want to make this bigger, if I want to increase it, which one of these should I change? If I want to make this move out more, if I want to increase the amplitude, what should I do here? Okay, so you're going with increase this. Okay. Any other answers? Are we all happy with that?
W. What is that? No, I think it's what
Increase this. Okay, you're going to say increase this. Okay, well, anybody want to go for this answer here?
No.
Go for it.
You go for it, KJ. Thank you. Okay, good. We have all 4 answers. Increase all of these.
Oh, correct.
Does anybody want to suggest maybe decrease any of them? We're ruling decrease off the table. Decrease not going to be it. Okay. So this one here, no. This one, no. This one,
No.
no. This one,
No.
no. So that hasn't worked. This might be a bit of a surprise. So now you're going for decrease, is it? Decrease, no. Decrease, no. Decrease, no. Decrease, no.
No.
Now remember, so F equals minus m omega squared S. So to increase the force is the same thing as increasing the omega or the S, which we already said no to. So not that. Good try though. No! Surprisingly, but maybe after I tell you it'll make sense, we don't increase the F. We don't decrease the F. We make the F the same for both. Or, because 1 over F equals T, we could say we make the T the same. Or, because T equals 2 pi over omega, we can say make omega the same. In other words, by matching the frequency between them, we can increase the amplitude of the smaller one. It could be, or it might not have to be. It doesn't need to be actually. It could be smaller, bigger, or the same. Not important. Yeah. Changing the A will have no effect on the A here. The only thing we really want to do to change the amplitude is to match the frequency. By matching the frequency, we can increase the amplitude, which might be a surprise, or maybe not when you think about it, because we have something in physics called resonance, which is what's happening here. I'll give you a picture now. The F, the omega, and the T, they do not change in the forced harmonic motion. Only the A changes. And how does the A change? Well, the A changes depending on the frequency. So, in this picture here, I think I call the F0 the frequency of this. So, if you increase the frequency until you match it to this frequency, then you have more amplitude. Then if you start to decrease the frequency past this point, if you continue to increase the frequency past this point, what happens to your amplitude? It goes down. So interestingly, if I increase the frequency to match this, I can make more amplitude. But if I increase it too much, I start to lose amplitude. So this is quite an interesting result. To get the most amplitude here, it does not mean move this faster. It just means move it so the frequencies match. This gives us most amplitude. An important result in physics. In the exam, they will ask you possibly to draw this graph. And also the name of this situation. Forced harmonic oscillator. The force being, this is an extra force on it. And again, just to say, the F here doesn't change. Even though I could be making this go further left and right, I cannot affect the F and the omega and the T. I cannot change that. No matter what I do here, I cannot change the F, the omega, the T. I can change the A, but in a very special way only.
Teacher, what if there is a friction between the
Oh yeah, okay. We're not looking at friction. Yeah, this is not. This is undamped. Oh, can it go backwards? I don't really know, because what's happening in this picture here, Monica, is that this particle, can you see, it's free. And this particle here, there's a piston, there's a force moving it back and forth that you can change. So, to answer your question, yes, but that means you then have to grab this to shake it. And really all you've done then is you've swapped the role of this one being the forcer onto the other one. Okay, continue?
No.
No? Okay. We're waiting for 3 people. Don't make the picture too beautiful now. Come on, come on. Okay. Continue. Bruce? Okay. Right, so now after all this work and theory, we can finally have a look at some questions. A boy pulls a spring down 5 centimeters, so he pulls a spring down 5 centimeters and releases, and the spring begins to vibrate. It takes half a second for the spring to complete one oscillation. What is the omega? And how fast is the spring moving after 1 second? So let me draw the picture for you. We can do this one together. So we have something here, and then the boy pulls it down 5 centimeters, like this, and then it will start to oscillate up, down, up, down, up, down. I also tell you that the T is half a second. What is the omega? Okay, so let's think about our formulas. The easiest one would be just this one. We can use this. So omega is 2 pi over T, 2 pi over 0.5, 4 pi, what's that, 369, 12.56 with 12.56 plus 30, 60, 120, 12.572, is it? Can someone help us out? Come on, help a teacher out who doesn't have a calculator. 4 pi, what is it? 12.572?
566.
Oh, that's close. 12.566.
Yeah.
Okay.
So why T?
I said it in the question. Yeah. Okay. Next, I want the rads per second. Yeah. Next, I want the clip. Next, I want the V, isn't it? What is the, how fast is the spring moving after 1 second? V equals omega A. Now is it cos or sine? Which is it? It's sine. It's minus sine. I said minus earlier, didn't I? Because it starts from the outside. But we have a small problem. Dun, 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 dun. If it starts from the outside here, then I'm calling this plus and this minus. So just be careful of that. My answer, if it's a minus, means it's going up, and a plus means it's going down. Because of how it's drawn. So just remember, minus in this picture is up and plus is down. Okay. Also, we must make sure our calculator is in radian mode. So the answer would be V equals 12.566 with a minus 0.05 sine 12.566. Right? That's going to be 0, is it? It's at rest. But of course you knew it was at rest. Because what's the periodic time? Half a second. So after 1 second, what has it done? It's gone up and down twice. So of course it's at rest, because it's back at the start for the second time.
Means negative 0 something. Negative 0.1.
It should really be exactly 0. It's just nearly 0. Are you in rad mode? You need to be in rad mode. How? Oh. Shift mode rad? Continue? 1 sec.
What means outside, inside?
What's the difference?
Yeah.
So, if it starts from here, then we say this is outside. If it starts here, we say it's inside. Yeah. Depends where it starts. Okay, continue?
Calculation is 0,
Yep.
Why is it 0?
What do you mean, why? Did you put it on?
Oh, it's 0.0.
Yeah. But did you put it on the calculator?
But it's not 0.
What is it on the calculator?
Negative 0.14.
Close to 0. Are you in radian mode, Lee?
Sorry?
Are you in radian mode on the calculator?
Why is radian mode?
Then the answer is no.
Where do we find this one? Which one?
What's wrong?
Why is the different radian mode and floating mode?
Oh my goodness!
It becomes worse. 2 point something.
Yeah, that's practically 0. 10 to the minus 4. 0.0002. Yeah. So that's right. You could in the exam, that'd be fine.
Teacher, how do we get the 8? 0.05.
It's given in the question. That's a good question though. Right, continue.
Do we have to use radian mode every time we do it?
Yes!
Why is it?
Why is it?
Because as I told you in the last lesson, these formulas only work in radian mode.
All of them.
All simple and circle, yeah.
Circular one too.
Yes.
As I mean circular.
Yes, yeah. Okay, I need to continue. Right. Let me give you one to try now. A molecule is vibrating with a frequency of 1420 megahertz. The amplitude is 2.93 times 10 to the minus 15 meters. What is the omega? Go. Okay, let's have a look. No, I'm just doing part A first. What do you mean, wait? The omega... Look, the omega is 2 pi over t. Yeah. So the omega is 2 pi over t, which is 2 pi 1 over f, which is 2 pi f. So that will be... 1420 times 10 power 6 times 2 pi. I hope you remembered the 6. Yeah? That's quite large. I think I should put it back into megas. Ugh. Gigas? 8.92 gigaradians per second. Giga. No. Yes. Giga. Okay. B. Yeah. What is the maximum velocity?
Half angular. No.
We have to find the angle.
Half
Not quite.
and
Well, look.
after S.
You have two formulas for velocity. V equals plus or minus, which we don't care about if we want a maximum, omega root a squared minus s squared, or you have V equals a omega cos omega t, or minus a omega sine omega t, but you don't care about the minus. So which formula to use? You can use all of them if you wanted to, you get the same answer. The V will be biggest when this is 0. We can't change these. So that's omega A. The V will be biggest when this is 1. Because this is the biggest it can be. We can't change this. The V will be biggest when this is 1. Because we can't change this. So in all cases, the maximum velocity is A omega. We already have the omega. We know omega. It was the omega was 8.92 times 10 to the 9. So now we just need to multiply it by A, which is 2.93 minus 15. Okay, so that will be 10 minus 6, isn't it? What's that, please? So 26.1 micrometers per second. No, micro, yes, sorry. I thought it was nano. Okay, now that you have this basic idea, maybe you can answer the last part. What is the maximum acceleration? So which formula gives us acceleration? And we don't care about the minus. And what's the biggest that this could be? Can we change omega? No. The S changes. So how to make this biggest? You make S biggest. Very good, Jerry. Amplitude. So it's 8.92 times 10 to the 9 squared times 2.93 times 10 to the minus 15. Whew, what's that? So 8.92 times 8.92 times 2.93 times 10 to the 18 minus 15, which is 3. Yeah, so what do we get here? 81. 233.13. 10 to the 3? Yeah. Go for it, Sean. 2.33 watts. Or maybe we can stick with 233. What's this one called? Yeah, which is what letter? You know this one. Which is called?
Kilo.
Very good. So this is kilometers per second squared.
Do you have to have a kilo below?
You do not have to.
I prefer that.
You prefer this?
Yeah.
Okay.
No, I prefer that. I'm cubic.
Okay. Well, we don't care about the minus because I asked for the biggest, meaning the size. I don't care about the direction. Okay, continue. So, finally, a car's shock absorber. Does anyone know what that is in the car? It's very good, the suspension. Very good. Its mass is 2 kilograms and it vibrates twice per second and it compresses by 2 centimeters. So it compresses by 2 centimeters. How much energy is stored? Well, we just use our formula for potential energy. What is it? A half m omega squared s squared. Okay. Try this one now. Got an answer? Nineteen what? Aha, 2 pi over t squared a squared. So that is 4 pi squared a squared over t squared. That's 3.1415 squared 0.02 squared. What's the time? 0.5 squared. What's this? Do we have an answer? No answer? Pi squared, 0.02 squared, 0.5 squared. Syntax error. Quite small.
0.3.
Yeah. 63.17 millijoules. Yeah. Yes. The question? Yep. Yeah? Okay. Yeah. Let's just have a look here. I'll just put that minus in. Okay, let me just give you these. What is it? Homework. It is homework. What are you talking about? Here, enjoy. Yes.
I don't have that in our example.
Yes. Yes. Here,
how I'm going to do that.
No.
We don't have it.
Wait, Jerry. Just so you know, before we finish, there is one topic left in mechanics, which we'll do. When's our next physics class? Tuesday. We have a Tuesday, Wednesday, Friday. So we'll finish the mechanics on Tuesday. We will have a revision class then Wednesday or Tuesday or both, and then the last physics class will be the test of the mechanics. So that means everything will be on the test. What I'm going to do, I think we have how many lessons here? There are 20, 21, 22, there are 23 topics over 25 lessons. So your exam, I'm sorry to tell you this, it's going to kill you, will be 23 questions.
From each topic.
You've worked it out. One from each.
But the hardest one?
Ah, come on, I have some heart. Come on. You think I'm going to sit down and pick the hardest question and give it to you 23 times? Now, come on.
Yeah.
It's okay.
I will tell you that the 23 questions, they'll all be single answer, single part, not multi-part. You know what I mean? Okay, yes.
Maybe some of them.
Just okay.
None of them.
Stop.
None of them. 23 questions is enough, I believe.
Okay.
Perfect.
Okay.